In 2022, a team at the University of Calgary tracked 17 astronauts after they returned from the International Space Station. 12 months later, 9 of them still had not recovered the bone they lost. Not most of it. Not a percentage that rounds up nicely. They were missing the equivalent of a decade of normal aging compressed into 6 months. And an ISS stay is the short version. A Mars mission would last 5 to 6 times longer. So the question is not whether the human body can survive Mars. The question is at what point it stops being able to come back. This is a timeline of that process. Month by month, system by system. Until we reach the moment when the door closes and the body you left Earth with no longer exists. The standard Mars mission runs roughly 1,000 days, 7 months to get there, 18 months on the surface, waiting for the planets to realign, 7 months back, about 2 years and 8 months. And for almost all of it, in a gravity your body was never built for. During the outbound flight, 0 gravity. On Mars, 0.38 G, just over a third of what you feel right now sitting in your chair. On the return flight, 0 gravity again. Then you land. Full Earth gravity. 1 G. And your body has to remember how to function in all of it. What follows is a reconstruction of what the data tells us will happen. Some of it comes from the ISS, some from bed rest studies, some from mice, some from a single stubborn Russian cosmonaut who spent 437 days in orbit specifically to prove that a Mars flight was survivable. He had a point. But the data he generated also has a darker reading, if you look at it carefully enough. Within hours of leaving Earth, the body begins to redistribute, without gravity pulling blood downward up to 2 liters of fluid shift from the legs toward the chest and head. The face swells. The legs thin out. Astronauts call it puffy face, chicken legs. It is not a flattering combination, but at this point, looking good is no longer on the mission brief. What is less visible is what the fluid shift does inside the skull. Intracranial pressure rises. The back of the eyeball begins to flatten. NASA has a name for this. Spaceflight-associated neuroocular syndrome, SANS. Symptoms can appear as early as 3 weeks in. Up to 70% of astronauts on long missions develop some form of it. And SANS has no equivalent on Earth. It is not a disease we know how to treat. It is something that only happens in space. Meanwhile, the spine elongates without gravity compressing the discs. The average astronaut grows 3 to 5 centimeters taller. On the bright side, you will finally be taller than your brother for about 7 months. 68% report back pain. Most of it fades. But the risk of a herniated disc after landing is 4.3 times higher than the general population. At this point, everything is still reversible. The body is confused, but not yet damaged. By the end of the first month, bone loss becomes measurable. The proximal femur, the top of the thigh bone where hip fractures happen, loses roughly 1.5% of its mineral density per month. The lumbar spine, about 0.9%. These are averages from a meta-analysis of 148 astronauts across 25 studies. It is worth pausing here, because these numbers get misused constantly. Some sources will tell you that astronauts lose 1 to 3% per month, and then multiply that by 12, and announce 36% after a year. That math is wrong. Bone loss is not linear. It decelerates. The body does not simply dissolve its own skeleton at a fixed rate. But the loss is real, it is significant, and it is roughly 10 times faster than what an elderly person on Earth experiences from osteoporosis. In 3 months, the astronaut's hip has aged the way a 70-year-old's might over 3 years. Except the astronaut is probably 35, and the return flight has not even started. Muscle atrophy follows a similar curve but moves faster. The quadriceps lose about 12% over 6 months. The calves, 13%. The back muscles are hit hardest, losing up to 20% of their functional cross-section. And here is the part that rarely gets mentioned. The type of muscle fiber changes. Slow twitch endurance fibers convert to fast twitch fibers, the kind that fatigue quickly. The body is not just losing muscle. It is rebuilding what remains into something less suited for sustained effort. By month 3, the immune system has also shifted. NASA data shows that 96% of ISS astronauts shed reactivated Epstein-Barr virus. 61% show cytomegalovirus reactivation. The immune system is not collapsing, but it is distracted. Stress hormones are elevated. Natural killer cells function less efficiently and remain weakened for up to 60 days after return. None of this is visible. The astronaut feels mostly fine. They exercise 2.5 hours a day, 6 days a week. But inside, several systems are losing ground at the same time, and the exercise is slowing the decline, not stopping it. 7 months in, the astronaut has traveled somewhere between 55 million and 400 million kilometers, depending on the orbital geometry. The radio delay to Earth is now up to 22 minutes one way. A medical question takes 44 minutes to get an answer. If you break your femur out here, the emergency room is not on another floor. It is on another planet. And the ambulance does not come until the orbits align, which could be over a year from now. On arrival, the astronaut steps onto Mars. Gravity returns, partially. At 0.38 g, you weigh about a third of what you do on Earth. Walking is possible, but the body has spent 7 months expecting 0. But the data raises a question that does not have a comfortable answer. 0.38 g may not be enough. Studies by Mortreau and Ploutz-Snyder place the threshold for preventing muscle and bone loss somewhere between 0.5 and 0.75 g. Mars falls below both estimates, which means the body most likely keeps degrading even while standing on solid ground, just more slowly. From the outside, the mission looks like success. The astronaut exercises daily, works, builds. The spine has stabilized, the vestibular system has adapted, the puffy face has resolved. But what has accumulated beneath the surface is harder to see and harder to fix. By a standard conjunction class model, the total radiation dose for the full mission will approach 1 sievert. For context, NASA's career limit for astronauts in low Earth orbit was 600 millisieverts. A Mars mission exceeds that before the astronaut even begins the return trip. On the Martian surface, the daily dose is 0.64 millisieverts because Mars has almost no magnetic field and an atmosphere about 1% as dense as Earth's. That is the equivalent of getting a chest X-ray every 5 days for a year and a half. No one would volunteer for that regime at a hospital. Here, it is just the background. The cancer risk from 1 sievert is conventionally estimated at a 5% increase in lifetime fatal cancer probability. But Francis Cucinotta at the University of Nevada applied a bystander effect model and predicted the real figure could be double that. And there's no way to shield against galactic cosmic rays with current technology. Adding thicker shielding can actually make things worse by generating secondary radiation. Then there is the brain. This is where I should be honest about the limits of the data, because most of what we know comes from mice, not people, and that distinction matters. At University of California, Irvine, Charles Limley exposed rodents to simulated cosmic radiation. The neurons deformed, memory disrupted, anxiety increased. A model by Ivan Soltes at Stanford extrapolated those results to humans and estimated that roughly 1 in 5 astronauts on a Mars duration mission might develop heightened anxiety, and 1 in 3 might experience memory problems. No human has ever been exposed to deep space radiation for this long, so the honest answer is, we do not know. The closest data point is the ISS. In 2024, 25 crew members were assessed after 6-month stays. No significant neurodegeneration. Processing speed was slower. And 6 months in low orbit behind the Van Allen belts is not 3 years in open space. The mission is ending. The astronaut boards the return vehicle. 7 more months of zero gravity. By now, the cumulative bone loss in the hip and lower limbs is substantial. The PLOS-1 model from 2020, which used data from 69 astronauts, predicted that 100% of crew on a conjunction-class mission would develop osteopenia, the precursor to osteoporosis. 33% would cross into the risk zone for osteoporotic fracture. The heart has been working in reduced gravity mode for nearly 3 years. Earlier bed rest studies, which simulate weightlessness by keeping subjects horizontal for weeks, estimated up to 15% loss of cardiac mass over 3 months without exercise. But newer research from Benjamin Levine in 2023, studying 13 astronauts who actually flew, showed that rigorous exercise protocols can preserve heart mass over 6 months. Whether those protocols hold over 3 years is unknown. Scott Kelly's heart shrank slightly during his 340-day mission, but it continued functioning. He was also in low Earth orbit with daily resupply, a full gym, and the knowledge that rescue was hours away, not months. And even so, when NASA compared his biology to his identical twin Mark's, 7% of his gene expression changes had not returned to normal 6 months after landing. His telomeres, the protective caps on chromosomes, the ones that normally shorten with age, had lengthened in space, then rapidly shortened after return, leaving him with more critically short telomeres than before he left. 340 days. 1/3 of a Mars mission. The astronaut lands. Full gravity. After roughly 1,000 days of reduced or absent gravitational loading, the skeleton is porous, the muscles are atrophied, the cardiovascular system has remodeled itself for a lighter world. 80 to 83% of astronauts returning from long ISS missions cannot pass a simple 10-minute tilt table test. 5 out of 6 cosmonauts returning from Mir could not stand for 10 minutes without nearly losing consciousness. These were people who passed every fitness test NASA and Roscosmos could design. On Earth, they needed a chair. On Earth, they recover. 1 day, sometimes 2, and they can stand. Within months, most of them feel almost normal. But the Calgary study I mentioned at the beginning used high-resolution CT scans that see what standard bone density tests miss. The microarchitecture of the bone, the internal scaffolding, does not fully rebuild. Even years later, structural deficits persist. Astronauts who flew missions longer than 6 months had a 3.9% deficit in bone strength a full year after landing. Those who flew shorter missions had lost only 0.4%. Now scale that to a 1,000-day mission. There is a counter-argument, and it is a strong one. Valery Polyakov spent 437 consecutive days aboard the Mir space station in 1994 and 1995. He was 51 years old. He had volunteered specifically to prove that a long-duration flight was medically survivable, and he designed his own exercise protocol around that goal. Hours on the bicycle ergometer every day, calcium supplements, relentless discipline. When the capsule landed, he refused help, stood up, and walked. His first words, "We can fly to Mars." He lived another 27 years, dying in 2022 at 80. His survival is real data, but it is one data point in low Earth orbit with resupply with communication delays measured in seconds. It does not tell us what happens after. 32 months of weightlessness and partial gravity, with a severed of deep space radiation, and with the nearest human being who is not on your crew standing on a planet you may never see again. There is a solution that almost certainly works: artificial gravity generated by rotating the spacecraft. The physics is straightforward. Spin a vessel at the right radius and speed, and you simulate any gravitational load you want. But as of today, not a single human being has ever been tested in an artificial gravity environment in space. Not once. The optimal rotation speed, the minimum radius, the side effects of Coriolis forces on the inner ear, none of it has been validated with human subjects off Earth. The recommended radius for comfortable rotation sits between 50 and 225 meters. That is a structure larger than most buildings. It will almost certainly be built eventually. But it has not been built yet. And until it is, the timeline I have just described is what a Mars astronaut faces with current technology. The first astronaut who walks on Mars will know all of this. They will have read the bone density studies and the radiation models and the mouse data on neuronal deformation. They will know that their skeleton will weaken, that their eyes may change, that their heart will shrink, that their DNA will accumulate damage that no one fully understands yet. They will know that returning to Earth, if they return at all, means landing in a body that is no longer built for the place they came from. And they will go anyway. 1,000 days later, they step out of the return capsule. The wind is not filtered. The sky is not red. The ground holds them with a force they had almost forgotten. Their bones are porous. Their muscles rebuilt for a lighter world. Their heart has to relearn what 1G demands. And yet, they did it. Not because the body was ready. It was not. They went because something in us needs to know what is out there, even when the cost is the body that carried us. In that moment, standing on the ground that built them, they will feel what their mind already knew. This is the only place the human body was ever designed to be. And leaving it anyway might be the most human thing about us. Whether that is courage or recklessness is not for them to answer. That question belongs to whoever is watching from Earth, deciding whether it was worth it.